Welcome to our fourth physics lesson. This one's on position time graphs. We're going to look at these and we're going to compare them to velocity time graphs in the future. In this lesson, we are going to recognize a position time graph, know that you're looking at one. We're going to know the slope and what that means. We're going to look at flat, curved, slope lines and what they mean on a position time graph. We'll be able to recognize the motion, what type of motion on a position time graph, and you'll be able to solve problems using information off a position time graph, just like you were in a previous lesson using the information in a word problem. So let's look at the first thing. Position time graphs show the way you can recognize it. First of all, is that you have some sort of position, some sort of meters, the distance. They'll have an origin, which will usually be some sort of line that represents the origin, maybe the 0 point. We're going to have a time that's going on. And the position time graph, the main thing we're looking for is that you have meters on this y-axis. And then for a velocity time graph, which we'll cover in a later section, you'll see meters per second, and which is a velocity, and that's the main reason why you get the velocity time graph name. The y-axis, once again, the up and down is going to determine which one you have. So you have to be careful and watch for what information you're given. Don't just do a problem because you see some sort of line that you think you recognize. You need to think through meters per second over here. You have to think through meters per second over here, or changing velocity. Whereas this is just, if you're going up, you're going forward. If you're going down, you're going backwards. It's pretty easy to see. This one, if you're going up, you're going faster. If you're going back, you're going slower. And so we'll see those in a future lesson. Okay, so just be aware that the change in position, you might hear me say just the change in position or displacement. They're interchangeable words. They mean the same. They're going to be both on the y-axis, like I said before, and time's always going to be on the x-axis. Positions where you're located, and displacement means how far you are from a prior position with a direction from start to finish. So we have a few things, a few variables that you may have to, you might use to solve. These ones are fairly easy. If your x variable that we may use in an equation stands for displacement, xi stands for initial position, xf stands for final position. And so if we were ever trying to figure out how far someone traveled, we would just look at the numbers that would be on this line right here, and we would just kind of travel up, because this would be your final position and this would be your initial position. You'll see what I mean in a second. Okay, so just some of the shapes that you should recognize. If you have ever a flat line on a position time graph, and I like to throw numbers in so you can think about this. Let's just say this was 5 meters. Well, by the time you get to the end, you're still at 5 meters. So you're at rest. You have no velocity whatsoever. Positive slope on a position time graph means positive velocity. So once again, throwing in numbers, 2 meters, and let's say this is 5 meters. So you went from 2 meters to 5 meters, but you went at a constant rate. We'll talk about slope exactly and learn how to calculate information when we're given times too. But once again, the numbers kind of let you see what's happening. You can't just think 2. You need to think 2 meters. You can't just think 5. You need to think 5 meters. So you went from 2 meters to 5 meters. A negative slope, let me just erase this so I can keep on going. A negative slope on a position time graph is constant backward motion. Like, let's say this is 5 meters, this is 2 meters. You went from 5 meters to 2 meters, but at a constant rate. This straight line just means constant something, but in this case, it's going to be a constant velocity, but it'd be backwards here. When you have a curved line, if it's curved up, well, depending on how, there's different things that can happen here, but in general, looking at this one right here, you are moving forward because you're going in an upward direction, but you're not just going in an upward direction, you are going faster and faster and faster in an upward direction. Whereas this one, you're still going forward, so you're going forward, but you're going slower and slower and slower and slower and slower in that forward direction. If this continued, at some point in time, you'd stop, and you probably would keep on going. You'd reverse yourself, and this would be a different type of motion. We'll look at that in some of our practice problems later. So here's your first question. Go ahead and answer this question. Pause it. Which of these is a position time graph? A is going to be a position time graph once again because you look at the y-axis and you see meters, which is a position. What MKS unit on the is on the y-axis? What is the MKS unit on the y-axis of a position time graph? Well, in that case, it's going to be meters. What does the slope of a position time graph represent? This is going to be, when you want to think about it, meters over seconds. Slope is rise, or meters in this case. The rise is meters, and the run is seconds. So you throw that together into a unit, and you get meters per second. And meters per second is a unit for velocity, so that's one way to remember that. What kind of motion is happening here? So go ahead and answer that question. Answer the question, where did this object start? And answer the question, where was the object in the graph after 8 seconds? Okay, so let me just go ahead and explain what happened. So we have numbers here. Just looking at this person was going at a constant rate. They started at a 4 meter, around 4, maybe 4.5-ish, meter point. And they went all the way to a point that was maybe, so they went forward. As they're going up, they're going forward, and they went to maybe 9 meters. So they went from 4 to 9 meters at a constant rate. So this is going to be constant velocity, moving forward, positive velocity. One's going upwards is moving forward. Where did this object start? About 4.5 meters-ish right there. And where was the object after 6 seconds? So it was around 6 meters. And this is how you would find out. You would start at 8, and then you would go ahead and travel up, travel over, and find out where it was. And somewhere around 6 meters was where they were. Okay, what kind of motion is happening here? Well, you should notice that it's going, let's say this is time 0, it's going backwards. It's not going backwards, just backwards. It's speeding up backwards. So that curved backwards, the slope is increasing, but in a negative, it's increasing in a negative, or it's becoming more negative. Okay, so this next section, all I want you to do is I want you to draw the shape of the line, and we're going to look at some motion going on. And so I'll give you this first one, straight flying graph at rest. So if I want to do this, doesn't matter where I put it, but I would have a straight line sideways. So anywhere over there, and that would show rest. So that's what I want you to do in these sections. And this space is for any notes you may have. But this is what if you printed out the worksheet, this is what you'd have, or if you have the worksheet that I gave you. If not, draw just a quick, just draw a quick line. I'd put PM in meters and time in seconds. Or actually, let's go ahead and make this X if I was going to do it that way. So that if you don't have this handout, just do a quick graph doing that. Okay, so first one, if you take a look, this person's at 12 meters and he never moves. And so that's what's happening right here. Time's ticking away, but he never moves. He never leaves the 12-meter point. Next one, okay, he starts and he goes at a constant rate. He's never changing his velocity, and so that's what's happening here. And you can tell he gets all the way to the 24-meter point. Once again, this is 24 meters because it takes on that unit. So it's a straight positive slope line. So let's take a look at what happened here. So this guy looks like he's doing the moonwalk. He started at 16 meters and he's going all the way back and back and back and back. And at this point in time, he stops at the 2-meter mark. So once again, starts at 16 meters. And he gets all the way to the 2-meter mark. And it's a constant rate, and that's why that straight flat line, see how it's going straight down like this? Negative slope line, that's what we call it. Okay, and so now when we have acceleration, he's going forward, notice what's happening to this graph. It's getting faster and faster and faster, just like he is. The slope's increasing, increasing. His velocity, which is represented by the slope, is getting faster and faster and faster. He's accelerating this whole time. He's moving forward because it's going up, and he's moving forward faster. Okay, so now we have decreasing, he's decelerating while moving forward. So it's still going up, but notice how the slope is going downwards, just like he's slowing down, the slope or the velocity is decreasing over time. So the slope over here is a lot higher than the slope over here. Okay, and so now we can work some problems with the position time graphs. And just like before, you might recognize constant motion, and you can go to this equation. Oh, not that one. You can go to this equation if you recognize constant motion. Don't know what happened there, a little glitch. Or you can go ahead and if you realize that you're speeding up or slowing down, you might need to go to one of our acceleration equations from before. But either ones can work. You just have to decide, do you have initial and a final velocity that are different? If you do, you're going to be going to these. If you have the same initial and final velocity, you can go to this one directly. If it's position or time, you're not going to do either of these. You're just going to read it. If they ask you what time does this happen or what Well, it could be a little bit more detailed to the question, but in general, they're saying what time is he at 6 meters? You would just look off the graph and read it. If they said at six seconds, where are you located? Then you would just look off the graph and find position. So we'll go ahead and do some practice problems. Okay, for first of all, go ahead and answer these questions. Describe the motion during interval AB. Describe the motion during interval BC. Then describe the motion during interval CD. Okay, so what I want you to notice in interval A, he is going from 0 meters to 20 meters at a constant rate. So forward constant velocity. So he traveled 20 meters that time. BC, notice that he's at 20 meters here. And so I can just write in numbers, 20 meters, 0 meters, 20 meters, let's say 25 meters. So from BC, he goes from 20 meters to 20 meters. That means he's at rest or not moving, stopped, anything you have like that would be fine. And then lastly, you go from 20 meters to 25 meters, but you're going at a constant rate. It's just, there's not a curve, it's just a straight slope line once again on a position time graph. Once you've had the velocity time graph lesson, you might want to come revisit this lesson because then you can compare. So forward constant velocity is happening right here. Okay, what was the object's displacement during the first 5 seconds? So we're looking at this point right here, what happened here, and he went 20 meters forward. So he started at 0, we got to 20. What was the position of the object at 10 seconds? So we're taking a look at this, and oh, guess what? We can just read it off the graph. And his position was 20 meters. Once again, position or time, most of the time you can read off the graph. Of a position time graph, not a velocity time graph. That in the future, you're going to get velocity off of those and time off of those. How far did the object move from 5 to 15 seconds? Okay. 5 to 15 seconds, once again, I could throw that information in there. Didn't move at all, 0 meters. What was the object's displacement from 15 seconds to 20 seconds? So I'm just looking at this point to this point. So where did they go from this point to that point? And that was about maybe 5 meters forward. Where was the object moving the fastest? Okay, so now you have to remember that slope is the velocity. And if you take a look right here versus right here, right there, the slope's a lot greater here. So it's going to be this AB interval. BC is going to be no slope, so they were at rest. So greatest positive slope in this case. Fastest forward. It's just something else to watch out for some problems. If they say, what was their speed? You have to look at the greatest slope and you have to ignore the sign. So for some reason, if they said speed and I had like this line right here, that would be definitely the winner. But if it said positive velocity, that's still the AB interval that I have right here. Let me just go ahead and say what I mean. So let's say this was the question right here. Where was the greatest positive speed? It's still going to be AB. But if the question said where was the fastest, the greatest positive velocity, it would be AB. But if they said what was the greatest speed, at actual D interval, the last little part right here I just drew in would have been the greatest speed because its slope is more than that. You ignore the sign. Okay, what was the velocity of an object at 3 seconds? So you have to watch out for these ones. These are not too difficult. It's actually a lot similar to what we did before. You need to find out, so this is 1, 2, 3, that looks like 3 right there. So it's asking you for the slope here, but you can't take the slope of a single line. So what you're going to do still, you're still going to take this entire interval. This slope is the same as a slope right here at this point, but you can't take this single point. So you're going to take this whole section. Careful not to go directly to this equation. Often there's going to be initial and a final velocity. And like if this is the CD interval, you need to watch out because sometimes people will put 20 for time, but this really would be a 5-second time interval. But we're just looking at AB right now. And we're going to go ahead and we're going to just pick off our information. We got 0 meters over here. We got 20 meters over here. We got the time it took was 5 seconds. And we get all this information, and with that, we can solve for the slope of this line. So it's pretty much using, we're finding the slope, but it's an equation. The v is nothing more than the change in velocity, and you can just look at this and say, oh, well, it went 20 up, so you can just plug in 20 there. But we're going to go ahead and pick this equation, and we're going to go ahead and plug in numbers there, or you might have just did it in your head and said that's 20. And then from there, you still have to write things on your paper. So on your paper, at least have v equals 20 over 5 if that's what you did. Don't just do it in your head. And then lastly, the answer is going to be 4 meters per second. So once again, you should be writing all this down. It's all about good practice and writing out a givens list. You're getting graded for some of this in the future. You're going to have to give me a givens list and take pictures of your work. So givens list, the work, equation chose from that givens list. So this is pretty much the progress. You get the givens list, you get the equation, you do the work, you get the answer, and then lastly, circle the final answer is usually a good idea so I can see everything you did. Okay, what was the velocity of the object at 10 seconds? So we go and find this 10 seconds, we find this, and you can take a look at it. Either you can do the math and say 20 minus 20 over 10, which you know, and if you just recognize the shape of a position time graph, it's going to be rest because it's a flat line. What was the velocity of the object from 15 to 20 seconds? So we're going to go ahead and go back with making a givens list. You start off with at 20 meters, you get to 25 meters, and the time it takes to get from there to there is 5 seconds. 20 minus 5 would give you 5 seconds. You plug it in to the velocity equation, or you realize you just have to do the slope of the line. Either way, it's going to be change in x over t, and you get your answer. The answer would be 1 meters per second. Okay, so go ahead and answer some of these questions. Describe the motion of the graph from 0 to 20 seconds. 0 to 20 seconds. I was showing you right there. So what was this motion? 0 to 20. And then secondly on B, what was from 0? So I didn't mean from 0 to 20. I have to change this. This should be the second one. I meant to say from 20 to 45 seconds. So that will be fixed up on the worksheet. So the first one, you're going constant forward from 0 to 20 seconds, constant velocity forward, and then after that, you're going constant velocity backwards from 20 to 45 seconds. And this is just a picture of what's going on right here. He starts at 0, so let's start it over again. Starts at 0, goes all the way to 30 meters, and then he goes backwards, and it's a constant rate. He doesn't change his constant rate after you pass this point right here. He's still going the same rate backwards. He just happens to be behind. He's past the origin at that point. So right here, right where this would equal 0, he was back where he started, or the origin, because he started at that origin point. So that's something just to note. Okay, what was the velocity of the object at 30 seconds? You're going to have to take the slope of the entire line. Once again, you can't take the slope of a point. And so you can just take information off the givens list or off the graph. You start off at 30 meters, you get to negative 20 meters. And the time it takes is right here. And so 25 seconds. You go from 20 to 45, so 45 minus 20 is 25 seconds. So that gave us that given. That's an S. Often why I leave off my S's when I do the math, especially with my chicken scratch. And then we go ahead and we just plug in our numbers. We pick our equation, we plug in our numbers, and we get an answer of negative 2 meters per second. So this could be 2 meters per second backwards. I'll take negative 2. If I'm not using directions, I'm not telling you this is east, west, forward, backwards, whatever. Just we'll assume if you give me a negative, I'll keep it as that. But that would represent backwards. Okay, what time was the object at rest? So go ahead and take a second and just think about this graph and go through 19 and 20 and 21. Okay, so the object is at rest somewhere around here, I would say. This is the flattest line that I can see. Around 6 to 7 seconds, somewhere in here he's at rest. There would be some sort of flat line somewhere in here. At what point did the object start decelerating? Well, he's going at a constant rate, and then maybe around here, he started seeing a little curve down. Maybe around 3 seconds. And then lastly, about what time did the object start accelerating backwards? So they stopped at that 6, 7 point. I think maybe a little past 7, around 7. you start seeing it curving downwards and getting faster and faster and faster and accelerating. So you're going in a downward direction, so you're going backwards. And then it's curving downwards, so the slope's increasing in a negative direction around 7. And then just remember, a reminder about the sign. So your V is negative because you're moving down. A is negative because it's curving down. And once again, on a position time graph.